I will be talking about StyleGAN 3. So this is a little bit strange for me to be talking about it because let's be honest, StyleGAN 3 is quite heavy in terms of signal processing content, and I am by no means an expert in that department. But still, I really wanted to tell you about it because it's just so interesting, and I don't usually need another reason. So I guess let's dive in. Just yeah, don't be too disappointed if I can't answer one question or the other because I simply don't have the background for it. So as you can see here, those are the two main papers that we are going to talk about. So on the left, analyzing and improving the image quality of StyleGAN, that's the StyleGAN 2 paper. And on the right, alias free generative adversarial networks, that is the StyleGAN 3 paper. Now, before we go too fast, let's first remind everyone what are the StyleGAN neural networks, just in case someone here is not aware of the latest GAN advances. So StyleGAN is basically an unconditional image generation model, and a very good one at that. Actually, it's one of the best ones that currently exist. It has really differentiated itself by creating those very high resolution and extremely realistic faces that are so impressive to the human mind, because faces are precisely one of those kind of images that the brain is very good at analyzing. So when we see a good face, we know that it's a good face. So it's that much more impressive that we actually manage to generate those kind of images. But not only that, actually, it has also provided very good image generators that are also disentangling some of those features. So for example, here, you can see that from a single source image A, you can couple the source image with the different sources B to mix and match those textures and content in a way so that, well, yeah, the images that you get out of this clearly keep some features from the source A and from the source B. And that's the kind of thing that, although it already existed at the time, it had never been seen before at this kind of level of precision. But now, what are we going to talk about today? Well, today is StyleGAN 3. And StyleGAN 3 involves rotations and translations. Now, it may not seem that impressive at this point, but let me tell you, the translation and rotation literature for GAN is not littered with successes, right? It is actually something that is very hard to do usually, and that researchers usually only succeed in if they are willing to compromise a lot with the quality, which is not going to be the case here. So you can expect some very interesting analysis. So let's go ahead with the next slide, in which I will talk a little bit more about what comes before StyleGAN 3. So the origin of the StyleGAN family is, well, everything that existed before that. And those usually looked like what you can see here on the left of the screen. So usually a generator that is not a style generator starts from a latent variable that is fed into the main body of the network. And then you will process this latent variable first at a certain low resolution, then upsample, process again, etc., etc. That is the conventional generator. Now, of course, there exists a lot of different versions of this. They mostly come down to this. And then we have the StyleGAN 1 generator, where already a lot of new things were implemented. First, you can see that if you don't mind showing it with your mouse here, we have a constant in the middle of the network, which so this is the const box, the green const box up there, which has replaced the latent variable as the input of the main body of the generator. Instead, the latent variable is fed on the side, so on the left side, through what is called the mapping network, and it is fed to the main body of the generator through specific kinds of layers, which are called adaptive instance normalization layers. So those layers, for those who are not aware, they will be some kind of normalization layers that actually accept two trainable parameters, which in this case are not trained, but rather provided by the mapping network. And finally, the StyleGAN 1 architecture ends with some noise being also fed um, at every scale of the architecture on the right. So that was StyleGAN 1. It was the main part of the breakthrough. And then StyleGAN 2 mainly focused on improving that. So in StyleGAN 2, we still have this constant that starts at the very top of the model, here denoted C1, but the rest is much more simplified and optimized. In that case, the latent is still fed through those A boxes that you can see here, even though the latent the latent part, the left part, is not represented here. And there is still some noise here denoted by the B boxes. So it is very similar in nature and in organization. It is very similar to what we had before, to the StyleGAN 1 architecture, except that now things are a little bit more streamlined, especially the adaptive instance normalization is now implicit and performed at the weight level instead of at the feature level. But otherwise, it's mostly the same thing. And this is the architecture we are going to start from and to work from in order to develop StyleGAN 3. So before we talk about StyleGAN 3, I would like actually to talk a little bit about the problem that StyleGAN 3 tries to solve. So if you can, actually we are going, I think, to share with you the link to this video that is here. It will be probably much easier for you to see that on your own screen because, yeah, through the screen sharing, it's not that good. So I just sent the link in the chat, but if you are watching this on YouTube, you may see the link in the video description instead. A very easy way to just reach that page is to just type alias FreeGAN on the internet and just click the first link. And then the first video on the project page is going to be this video. Now, I'm going to leave you a little bit of time to watch it, right? So if you can just start the video again on the slide, just so that we can watch it again. Okay, so here you should be able to see two parts. On the left, you have the StyleGAN 2 result when it is moved along, translated along in, well, the physical space. And on the right, you have the same translation, but operated on results from alias FreeGAN or StyleGAN 3. Now, uh, you may notice something very strange with the left result, which is that the texture does not move along with the face. And that goes for the texture of the beard, that goes for the texture of the hair, that goes for the texture of the skin. So for all of those parts of the texture, strangely, it doesn't stick. And well, that's kind of the base problem that StyleGAN 3 set out to solve. So if we have a look at what an image looks like, so here you will see an example of an image where I have represented the hair of a person as those purple pixels. And then you have the skin of the person as the yellow pixels. And I have also represented one independent strand of hair in light blue, as well as one independent fold of the skin in orange. Now, when this face translates in the image, you would expect those features, this strand of hair and this fold of the skin, to translate with the face, to translate with the bigger object. But actually, in StyleGAN 2, that's not what we see. Instead, it kind of looks like the features are stuck to a certain specific place, to a certain specific pixel coordinate, and that when the object happens to be at the same space, so for example, when the hair is at this location, then the strand of hair will activate and appear on the screen. However, when the skin is at this location, well, instead, the strand of hair will deactivate and the fold of the skin will activate. So to quote the paper, it's as if the texture element was stuck to the pixel coordinate and just activates or deactivates depending on what object, what part of the object is represented. So yeah, very strange situation. But what could this be? What could be the cause of this strange phenomenon? Well, in order for it to be able to figure out where it is in the image, because this happens because obviously the network is aware at which coordinate it is looking, which should not be the case, right? The convolutions, they are meant to apply the same operation to every pixel. So the convolution should not be aware of which pixel it's looking at. Why is it in practice the case that it knows where it is? Well, a first way to know that, a first way for the convolution to figure out where it is in the image is thanks to the boundary effects. So if we have a look at how a convolution filter is applied, if a convolution filter is applied with padding, which is the case in every single layer of the StyleGAN 2 generator, then a specific area of the feature map will contain only zeros. And this is a very clear indicator that the convolutional filter is currently at the border. So this kind of indicates that the border is here, and then from one layer to another, the perceptual field of the neural network will expand, and it can bring an information about the location in the image to basically any pixel after a few layers. So this is the first thing that they will want to avoid. The second thing is aliasing, which is a much trickier thing to solve, because it's also a much trickier problem to understand. So let's talk a little bit about it. So aliasing is a kind of sampling error that appears when the Shannon-Nyquist theorem is not satisfied. So we all know that images are represented as matrices. But we are also aware, of course, that those matrices, they are but a representation of some signal that is actually continuous. So how can we be sure that our matrix actually represents correctly that continuous signal? Well, the fact is we can't be sure, because the way we would have to be sure that this is actually a faithful representation is for the Shannon-Nyquist theorem to be satisfied. We're going to talk about that in a second. And in general, let me tell you, it is not. So one of the major reasons why this is not the case is, among other things, that the ReLU activations, which looks like this, contain some straight parts which basically introduce at every single layer of the network infinite frequencies into the signal. And this means that this theorem will never be satisfied, and therefore there will be aliasing problem, which means, again, representation problems between the matrix that we use to represent the signal and the signal itself. Now, why is this aliasing a problem in itself? Well, in a way, you can see this as aliasing is a problem in the way we represent the signal processing through the network. And in theory, the convolution should not contain any information about where it is in the image. So if it does contain such an information, it can only be because there was a signal processing mistake performed at some point. And this hypothesis will turn out to be true, because as we will see, when we get rid of this aliasing problem in the generator architecture, well, this problem of texture sticking will disappear. So let's have a look. As you may know, signal processing considers that it is possible to go from a discrete representation to a continuous representation and back using very simple operations. So to go from from the first to the second, you can just convolve this sync function. And then in order to go from a continuous representation to a discrete representation, of course, you just need to sample it. So in that case, you can just multiply it with a Dirac comb. So of course, this can be done, but it can only be done if such an operation is possible. And the Shannon-Nyquist theorem states that this operation will work in both directions without losing information if and only if the sampling rate of the discrete sampled signal is at least twice the highest frequency in the signal. So basically, what we need to do in our network to ensure that the signal is correctly processed is to ensure that at any point, the highest frequency in the underlying continuous signal is lower than half the sampling rate. Well, that is not an easy task. So let's go ahead and have a look at how we can actually do this. So the first thing that we are going to need to change is this constant that we have at the beginning, because obviously this in StyleGAN 2 is a learned constant, so it can contain basically arbitrary frequencies, and we don't know if that signal is correctly represented or not. So in StyleGAN 3, they replace this by Fourier features that are continuous by nature, and we can actually sample them however we want because we have a closed form of this function. So that is what is used. And actually, this is a very, very interesting change because just by replacing this constant by these Fourier features in StyleGAN 2, they actually achieve better quality and better performance by changing only that in the network. So this seems to be a very generally good thing for the StyleGAN architecture to replace this input. Okay, then next thing they had to do, and they weren't very happy to do that, but they had to, is removing the noise. Because basically, the noise has two problems. The first one is that it introduces high frequency signals, which we don't want. And a second, they also counteracts the capability of the generator to be translation equivariant because the noise itself is not translation equivariant. And remember, we want the generator to be translation equivariant because when the object moves, we want the generator to not care, right? We want the generator to be able to draw the object wherever it is on the picture, which should be the case since we are using convolutions. So that would be the second thing. And then the third thing we are going to need to modify is the upsampling method. So the upsampling method here is actually very simple to do if you have a well-behaved signal processing, because an upsampling is nothing more than a different. An upsampling is nothing more than a different sampling or having a look at different points in the continuous representation of the signal. So all you have to do is to convolve your perfect sinc function on the discrete signal that you have. You get your continuous representation under the form of a function, which you can then interrogate a little bit more, basically, to have a higher sampling rate. And this should be enough to upsample your image. Actually, you can do any resampling that you want of this image as long as you have a satisfied Shannon-Nyquist theorem. But as we mentioned, the main culprit in there, we have yet to talk about it because the main culprit is the ReLU activation. So let's talk a little bit about that. So the problem with the ReLU activation is that it is setting a whole area of the signal to just straight zero, and that has infinite frequency. So how could we basically do that? Well, ideally, what we would like to do is to have a low-pass filter go through that continuous signal to remove those very high frequencies, right? But the problem is we cannot do that because we cannot, in practice, in a computer, process a continuous signal. So we have to find a trick. And basically, the trick that they decided to use here is that instead of just using the continuous signal, where they basically said, okay, we don't have a continuous signal. Instead, we're going to have to approximate the continuous signal by upsampling the signal and saying that the upsampled signal is the continuous version, which is, of course, it sounds a little bit bad since we are going for a very theoretically good generator here, but they actually show that this method works very well even for times 2 upsampling. So even a times 2 upsampling is sufficient, and going to times 4 or times 8 does not actually yield any additional benefit. So quite interesting. And since we are still on this slide, I want to point out that the low pass filter that we are actually going to be using, you can see it is denoted with the same theta s as the theta s that denoted the sync operation. And that's because this sync operation is actually a good low pass filter for this purpose, if you are using it with the same S sampling rate as the sampling rate you were using for the discrete representation. But of course, for now, we have only talked about this theta s as a perfect sync filter. But this perfect sync filter has an infinite spatial span, right? And we don't have an infinitely large signal. We only have an image that is bounded. So we are going to need an approximation of this. Now, one way of doing this approximation, which is the way that they chose here, is to make this signal go through a Kaiser window. So here you can see representation of different Kaiser windows. The Kaiser window actually has a parameter which determines the size of the window, and here you have it for different sizes. In the case of this paper, they use a size of 6. Right. Um, so now let's talk a little bit about what the response of the signal to this windowed sync function. So first, the impulse response. Well, that's pretty easy, right? If you have a Dirac and you send this filter, you send it into this filter, well, you will have the sync function. Not exactly the sync function, actually the windowed sync function, but it will basically look like a sync, just like this. Okay, very simple. Now, what actually interests us here is the frequency response. So let's have a look at that. Here you can see that it behaves how you would think a low pass filter would behave, which means that the low frequencies are actually kept the same. So they are multiplied by 1. This is the left part of the curve. And then at around a certain point, which is called the cutoff frequency, FC, around this point, the frequency response is going to start dipping until it reaches a state where it has basically collapsed to 0. And the time that it takes to collapse to 0 is defined by this half width parameter fh. As it turns out, with a Kaiser windowed sync function, we can have an influence on both the cutoff frequency and the half width fh. So we have a lot of influence on how this filter will actually operate. But as we are going to see, having an influence on this is not going to be enough. Because, of course, what you would like to do in theory is have a very, very small half width so that the frequency collapses very fast. And then you would like your cutoff frequency to be exactly at the sampling rate divided by 2, so that you don't cut off frequencies that you would want to keep. But that is not going to be possible. Why? Because, of course, the Kaiser window is not perfect. It is just an approximation. It is a sorry, it is a spatially restricted window. So when you use a spatially restricted window, the transform of it in the Fourier domain is going to look like this. Basically, you have the central mode, which is basically what we want to keep. This is the kind of thing we want. But then, due to the impurity in the filter, it will generate rippling effects on both sides. And those rippling effects are actually going to have a high impact on the response to the filter. So if we have a look at the gain curve of this filter, you can see that the rippling effect can be seen on the gain, which means that after a certain frequency, well, the frequency will not be cut as much as it should have. There will be a ripple where the attenuation of the signal will be higher than it should be. And you might think, well, okay, but the ripple is only happening at minus 40 dB. minus 40 dB, it's still dividing the signal strength by 100. What can there remain to be at 100 attenuation, right? If you divide it by 100, there should be almost nothing left. Well, this is where one of the most impressive results of this study comes into play, because they actually discovered that dividing the signal by 100 is not nearly enough for the signal to be well behaved enough. But what I mean by that is that when they apply this kind of attenuation, minus 40 dB, uh, well, the texture sticking remains. Now, you might think, well, okay, maybe then this was not the right way of proceeding. But then they realize that if they use a better filter, a more precise filter, which brings the attenuation, has a larger attenuation, at some point the texture sticking disappears, which means that it is the correct method. It is how you should do it. But where did it start working? Well, that's one of the most impressive results of the paper. It starts working at minus 100 decibel. And for those of you who are familiar with signal processing, minus 100 decibel is an extreme attenuation. You divide the signal by a huge number to the point that the usual float number representations are almost not enough to keep it. Right. So it's pretty impressive. What this means in practice is that basically, if you leave the tiniest frequency in this domain, the network is going to be able to pick up that this frequency is there, and it will have a strong incentive in order to generate good looking images to amplify this tiny, tiny little remaining frequency to the point where it can actually use it to stick the texture. Which is, I believe, very, very impressive. So what we learn here is that the neural network doesn't care about the intensity of the signal. If it can use it, it will. So yeah, that's the first thing that's very impressive. Now let's talk a little bit more because, okay, let's assume that we have this minus 100 decibel gain, that it works, etc., etc. Now let's have a look at the image on the right here. The image on the right is a little bit disturbing at first because it's not how we are used to seeing a representation of a neural network. But if we talk a little bit about it, so on the left axis here, you will see the layers of the neural network: L0, L1, etc., up until L13. So those are the layers. And at each layer, we are going to look at the log of the frequency used. So the easiest part of this graph to figure out is the red part. The red line is going to show the sampling rate of the image. So basically, it's just the size of your matrix. So in that case, this means that basically the sampling rate used is going to increase over time, which makes total sense because what we want to do is to increase the resolution of the image as we go forward. And of course, increasing a resolution means that we increase the maximal frequency that we allow. And then you have the green curve. The green curve actually follows the red curve, except it always stays behind by a factor of 1 in log 2 scale. So this means that basically the red curve is always, the green curve, sorry, is always the red curve divided by 2. Now, this is, of course, not random. It is so that we can follow the Shannon-Nyquist theorem, which is why the stop band actually here represents Fc plus Fh. So if you remember, Fc is the cutoff frequency, where we have divided by 2 the frequency, and Fh is the width, which means it is the size of the window after which we consider that we have reached a correct attenuation, in that case, minus 100 dB. So here, with this green curve set where it is, we know for sure that all of the frequencies higher than they should be will be attenuated by minus 100 dB. And then we have the other curves. I will concentrate mostly on the blue one. The blue one shows how the cutoff frequency evolves through the network. As you can see, it is a very linear in log scale curve, and it's actually this parameter that the authors fixed in a very conscious way. So basically, they said, okay, this blue curve, it should look like that. In other words, our cutoff frequency should evolve in this way throughout the neural network. And then from that, they said, okay, but our minimum stop band that we allow should also evolve in a certain way. At the start of the network, this yellow line, the minimum stop band, it should be far away from the cutoff so that we are absolutely certain that the rippling effect don't have too much impact and that we actually remove all of those frequency, because at the start of the network there are a lot of layers after the first layers so the network has basically a lot of time to amplify the signal, and we don't want that. So at first the minimum stop band needs to be very large, and then as we go forward further into the network, we can afford to have a smaller band, because basically the neural network doesn't have too much computational power remaining in order to amplify the signal and to make use of it. So at the very end of the network, we can have this very, very thin remaining um, remaining stop band, which is basically explained by the fact that we want to keep those frequencies. We want the image to be as high resolution as possible, and we don't think that the network has the time to leverage that additional information that is going to go through, basically. And then from that, they can basically, from these blue and yellow line, that's how they figure out where the green line should be, and that's how they figure out where the red line should be. So it's very interesting, because instead of starting with the architecture of the network and saying, okay, we should double the sampling here and we should upsample here, here, and here, they do it the other way around. They say, okay, the frequency that we expect to keep should look like that, and therefore we should upsample here, here, and here. And this leads, for example, if you look at layer 4, there is only a single layer at the sampling rate 6 instead of 2, because that's just how it happened. Their network is not made so that you have 2 layers, then upsampling, then 2 layers, then upsampling, etc. That's not how it works. Here it is using another kind of heuristic, which is why sometimes you have 2 layers and then upsampling, and here you have only 1 layer and then upsampling again. So yeah, quite interesting stuff. Okay, let's move forward, because here, with all of that, you actually have a network that is translation equivariant. But I told you at the very beginning that it would also be rotation equivariant. So what kind of crazy stuff will they need to add to obtain this rotation equivariance? Well, actually, we are almost there. There are only 2 things remaining. The first thing that remains is to change the sync function that we have been using so far into basically the jink function, which is also known as the sombrero function for reasons that I don't need to explain. And basically, it's just the sync function, but rotated so that it's rotationally equivariant. And here we can take a little bit, we can take some time to wonder what could be the last modification to perform, right? Do we have a network that is entirely rotation equivariant? Well, if you think about it, there is one thing that is not at all rotation equivariant. It is only translation equivariant. It is the convolution that we are using. 3x3 convolutions are indeed translation equivariant. But for them to be rotation equivariant, it should mean that basically they can't be applied in that very discrete manner, right? Because a square will never be a circle. So the only way that remains for you to make this rotation equivariant is to just use 1x1 convolutions instead. And that's what they did. They just replaced all the 3x3 convolutions in their whole network by 1x1 convolutions. And there you might think, hold on a minute. Uh, there is a reason why we are using 3 by 3 convolutions, right? We want every layer to be able to pick up some neighborhood information and then to make use of that neighborhood information in order to process the signal. How can a generator even work if it's only ever using 1 by 1 convolution? It means all the pixels are independent from each other, and it means the output signal is just going to be an independent noise of pixels. But actually, it's not the case. And it's not the case thanks to the modifications that they performed before. If you remember, the way that they perform the activation function, the way that they perform the upsampling is using that sync function. And this sync function is a filter that takes into account the neighborhood information. So here, what they did actually is that they shifted the role of aggregating neighborhood information from those filters to a non-parametric function that is always the same. And that's very interesting if you think about it, because it means that you don't need that many parameters to parameterize your network, because all of this aggregating role is handled by a non-parametric function. And actually, they notice that when they do this, when they do this change, they need to double the number of filters, which is not a big deal because we just divided by 9 the size of the layers. So we can afford to double the number of filters. And when they do that, the network achieves even better quality than it used to before the change. So it's actually quite crazy if you think about it. They just removed a whole number of parameters from their layers, and suddenly it's better because the neighborhood aggregation part is handled by a principled way. It's kind of a return back to the handcrafted features if you think about it. It's kind of strange, but it works. Now, of course, it's not all pink, right? It's everything does not work perfectly in the best of worlds because it actually takes twice the time to train. But well, we can't have everything. So let's go very quickly over a few recap of everything we said, because we've said a lot of things. So from StyleGAN 2 on the first line, the first thing they did is they replaced the constant input by Fourier features. And this actually improved the FID. This also gave a first baseline for the translation and rotation equivariance, which from then on they tried to improve. So then they removed the noise because they thought that, well, we are going to remove the noise at some point anyways, so let's do that now. And here you can see something else that's interesting, but no time to go deeper into this, unfortunately, which is that even though the noise inputs are a significant part of the StyleGAN and StyleGAN 2 architecture, which they previously argued was an important part of it, it actually improves the FID to remove them. But well, let's pass on that for now. Then they simplified the generator. I did not talk about this. It's not too important. They just remove the parts that are going to make the generator non-translation equivariant. Those are not important parts. They are like regularizations most of the time. And you can see that here we start already seeing some improvement in terms of translation equivariance. So here, this translation equivariance metric used here, the higher, the better, basically. And then they start introducing their signal processing improvement methods. So first thing, they change the boundaries, right, to avoid the boundary effects, and they modify the upsampling method. They lose a lot of FID by doing that, but that's okay. We're going to earn it back later. And the translation equivariance improves as a result. Then they also handled the filtered nonlinearities, also losing some quality and also improving the equivariance. Then this non-critical sampling is what I told you about, the fact that they cannot rely on the cutoff frequency alone, because the cutoff frequency is at -6 decibel, and -6 decibel is not enough by a very long shot. So introducing non-critical sampling here basically means that they increase the size of the stop band, and they introduce this kind of linear modification of the cutoff frequency and the stop band minimal frequency in the graph that I showed you on the previous slide. And this has a very good effect both on the quality, because now the signal can actually proceed through the network correctly, and obviously for the same reason on the translation equivariance. And finally, the transformed Fourier features is something that I did not talk about yet, and we can have a look at it in the questions if you want, because I am running out of time very seriously. Okay, let's go over the flexible layers. It's basically kind of the same as the non-critical sampling. I kind of bundled those two together, so no need to spend further time on this. As you can see, the translation equivariance further improves even more. And the rotation equivariance basically does not change much except for two things. First, obviously, the rotational equivariance improves drastically. And very interestingly, as I previously mentioned already, the FID also improves, which is kind of ironic if you think about it. Okay, so let's have a look. Let's try to wrap this up as quickly as I can. Let's have a look at some visualizations. Uh, these here are some feature maps that they visualize from different parts of the network. So basically what they do is they choose a layer somewhere, they should choose 3 feature maps, and they just plot that as RGB channels of an image. So as you can see in the StyleGAN 2, the network has a very spatial-based internal representation of the image, and it doesn't need it can rely on the coordinate system of the image because it has access to the coordinate system of the image, so it doesn't need to store any coordinate-based information within the feature maps. Then on the second line, you have the translation equivariant version, where you see those strange lines start to appear, kind of like um, a bent coordinate system, right? A modified coordinate system appearing. And this is where you can really see that we shifted from a spatial-based generator to a frequency-based generator, right? This is really the thing that you can see right away. But otherwise, honestly, it's kind of hard to really interpret this image. Those lines, they make us think about some kind of coordinate system that is created by the neural network to figure out where it is. But is it actually that? What do they actually mean? It's a little bit hard to figure out. And then you can see that the rotational invariant network actually goes even further with that, because the lines are even more defined. They actually underline and go around some distinct features of the face, as if they wrapped around it and defined areas in the object that need to change. So yeah, it's a little bit hard to interpret, as I mentioned, but they are just so interesting to look at, and I find them so odd that I kind of had to show them to you. Okay, let's go ahead with the conclusion. So a few things to take away here. The first thing that I want to mention here is that basically this idea of introducing the Fourier features as the input, well, it was a very good idea, because by this alone, which is a very simple change, you can actually improve the quality of the network, as well as improve your network's controllability, because those Fourier features, they can be moved around and rotated in the input space to imply an equivalent translation or rotation in the output space, which is quite interesting. And for such a cheap trick, in a way, it gives great results. So it's the kind of thing that, as GAN designers, we want to know. Now, the second thing I want to talk about in this conclusion here, I don't remember which one is the second. Okay, thank you. Is this intensity, the fact that the intensity of a signal is not the importance of that signal. Now, those of you who know me personally may know that I have done a master thesis in neural network compression. And in neural network compression, it is often a heuristic used that if a part of the feature map or a certain weight in the neural network is small, then it's probably a weight that we can remove. But obviously, this is certainly not the case. The intensity and the importance are totally different, and the proof of that is here. Some very, very, very small signal will influence the network in huge ways, completely changing the way that the network is understanding and processing the signal. These very, very small frequencies can literally induce a change of a whole paradigm of the way the network is computing the signal. Third thing that I want to point out is obviously come back on those one by one convolutions because it was actually kind of impressive. And I really wonder now, seeing this work, is it something that we can generalize to other kind of neural networks? Could we design convolutional neural networks for example, classification that only use one by one convolution and thus are much more lightweight and only use parameterized operators to aggregate neighborhood information? That's actually something I would be very interested to know about, and I hope that the research will go in that direction in the future. And finally, the last thing I want to talk about is more of a personal concern of mine, which I already mentioned when I was talking about StyleGAN and StyleGAN 2 6 months ago. In the past century, science has taught us that uh, often things are a question of trade-offs. There are some things that are impossible to achieve. There are some kinds of information that we cannot reach because the world around us is made of those trade-offs. If you win somewhere, you have to lose somewhere else. And in these kind of works here, um, these kind of papers are those that remind us that although this may be true with some very old fields like math, like physics, AI is still very new. There's a lot of things we don't know, and we should not hinder ourselves and our own thinking processes by thinking that there's going to be a trade-off. If we win there, we have to lose here, and so on. It's so easy to get depressed to think that explainability cannot be achieved without a cost in quality. But there's not always a trade off because we're just not perfect yet. We haven't reached that point where we cannot improve. Sometimes we can just do better. Okay, that's all for this presentation. I hoped you like it, and well, of course, I would be very grateful if you have some question, and I would love to answer those.